Welcome to Chapter 6 in the IPv6 Fundamentals book. This book was written by Rick Graziani. All of the credit goes to him. These are his PowerPoints. This is his book. So with that said, he wrote both the IPv6 Fundamentals and the IPv6 Fundamentals videos. So again, all credit goes to him, his book, his videos, which you can purchase. I hear the ISBNs. Alright, so in Chapter 6, we're looking at multicast type addresses. So we're going to be looking at the purpose and the format of a multicast address for IPv6. Again, we've already done unicast, and now we're moving on to the next section, which is multicast, both assigned and solicited nodes. So the big thing here is, what is a multicast address? It is used by a device to send a single packet to multiple destinations, one to many. So if you're familiar with IPv4, same thing. Multicast in IPv4 is similar to multicast in IPv6. The big thing here is it's a one to many. So instead of having to send a one-to-one, a unicast, or a broadcast, one to everyone, I understand that in IPv6 we don't have broadcasts. I'm just saying we have those three general types. IPv4 is unicast, multicast, broadcast. IPv6 is unicast, multicast, and anycast. So it is equivalent to a 224.0.0.0/4 within the IPv4 network. Technically a class D used for multicast. There are two types, again, assigned and solicited nodes. I want to get a little bit more into that later in this chapter. So let's look at the source. The source will always be a unicast. The destination can vary depending on requirements, though. Again, the destination could be a unicast, could be a multicast, could be an anycast, because we're talking about IPv6 now. So again, source is always going to be unicast. Destination can vary. So multicast range is going to have a prefix of FF00 with a /8, meaning the first 8 bits are going to be tied together. The next 4 bits will be flags. The following 4 bits will be a scope. The scope is a 4-bit field used to define the range of the multicast packet. Because again, the purpose of the multicast packet is more of a one-to-many. RFC 4007 does lay out the scope address architecture. So again, the scope is a partial list. 0 is reserved, 1 is an interface loop, 2 is a loopback, 5 is a site local, 8 is an organizational loop, or organizational local scope. So there are predetermined prefixes or partial lists for our scope. And E, which is our global scope, will be the entire network. So I want to point that out again. Interface local, link local, layer 3 boundary. Site local could be anything attached to that router or that layer 3 device. Organizational local, and then global will encompass the internet as well. So flags, again, 4 bits. At the time of this recording, there is just a draft for this. So this book was written a little over a year ago. So that there probably is going to be more of a concrete RFC, which I've not found any information for our flags just of yet. So our flag is, again, 4 bits. 0 is going to be a permanent. It's a well-known multicast address. assigned by IANA. It includes both assigned and solicited nodes. One will be a non-permanent assigned or dynamically assigned address. And that could be something like an FF18, which is just a random one used for multicast within our organizational scope. So again, our solicited nodes are going to be something like FF02. A assigned node will be more like an FF00/8. Our 2375 deals with specifically multicast address assignments, and it defines the initial assignment of our multicast addresses, focusing on the permanent assigned global IDs. Here is again the IPv6 multicast address base registry from IANA. So let's look at our flags a little bit more in depth. Here we have a flag of 0, which is an assigned multicast, and we have a scope 2, which is link local. Which should be able to tell us that link local will be anything on that network. So other types of assigned multicast addresses with that link local scope should be able to look like this. Again, the predefined group, the compressed format, again, taking and organizing it correctly. And then depending on how we look at our group IDs, we could have a general description. Things like all devices, all routers, OSPF, the OSPF DRs, the RIP CIGRPs, and so forth. Interesting little tidbit, if you're familiar with multicast within OS or multicast within IPv4, if we're looking at the multicast version IPv6 portion of it for OSPF routers, you'll notice something very similar. Multicast IPv4 is a 224.0.0.5. Here, our multicast address is FF02::5. So they did try to keep a lot of the multicast numbers the same for IPv6 and IPv4, dealing with the last number. So that was just kind of a tidbit for you. A few more. If we're dealing with a site local scope, our routers, FF05::2, and again, all DHCP servers. That way we're able to quickly address specific items based off of our requirements. Interesting little tidbit is you need to enable IPv6 multicast routing, and when you do that, it will enable the PIM on all interfaces with the appropriate IPv6 address, meaning you do not have to explicitly configure it on every interface like we did with IPv4 multicast. So with that said, again, our scope, multicast routing, IPv6 relay agents, and multicast addresses are included in a little bit later lesson, I believe in 2 chapters. So IPv6, all devices assigned within that multicast address space. Again, we have to turn on IPv6 addressing by IPv6 unicast routing. That enables, again, IPv6. All of our devices within our multicast address will be a FF021. That is all devices. That includes things and routers and all of the appropriate groups. Every IPv6 device will listen and process packets specifically for this address, just like, again, IPv4 would. Is this the same as a broadcast? No. The important differences between the two is it maps to a layer 2 MAC address, which is more efficient. And that's really the big thing, but there's a huge part of that. So we're going to talk about that coming up, but It's similar to a broadcast, even though it's not the same. So again, FF02:2 is all routers. That will, again, all routers will process requests with these packets. It is used by devices to communicate with an IPv6 router or routers. So we can verify the appropriate multicast addresses are on the routers by doing something like a show IPv6 interface and the appropriate interface. If IPv6 is enabled on that interface, then you should be able to see the appropriate joined groups. And they should also then list the appropriate multicast addresses that they're familiar with. Once we assigned a global unique address to this interface, that's how we got the appropriate all IPv devices, the FF021. We will get the FF025 once we actually enable OSPF version 3 on this interface. So as we start enabling certain features, our interfaces will automatically join appropriate multicast groups based off of requirements. So moving on. OSP version 3, that DR router. And solicited nodes, we're going to be talking about that coming up shortly. So what is a solicited node in multicast? That is a big thing. We have our entire next section of this chapter dedicated to just that. So an interesting little tidbit from Keith Barker in CBT Nuggets was when we create a solicited node multicast address, we actually link it. So when an interface shares both a global unique address and a multicast type address, we can actually have them linked to one another. So in addition, every unicast address is assigned an interface. This device will have a special multicast address known as that solicited node multicast address. It takes the unique unicast address, IPv6 address assigned to that interface, and then it maps it to that special multicast address. So unicast, global unicast address, and link local addresses all will be mapped to those solicited nodes. So here we have a unicast address. Again, a layer 3 multicast address. It has to begin with FF02. There is a solicited node multicast address for every IPv6 unicast or any cast type address, unicast, link local, and here they go. Basically, they allow us to map our addresses. Normally, the last 24 bits will be the ones that we're mapping. So when we use things like ICMP version 6 for neighbor discovery messages, we do things like the address resolution, which is similar to ARP, and we also do duplicate address detection, DAD, which is similar to, I can't even pronounce that word, ARP. Gratuitous ARP. Basically, it just verifies our address lookups and address duplication. The important thing here to realize is, again, you're going to end up with a multicast address per individual unicast address for our solicited nodes. How is it created? So there is a direct relationship between unicast and unicast addresses and its solicited node address. The solicited node forms it normally by, again, that remaining last 20-ish bits. I've heard several reports 20, and I've also heard several reports of 24. So realistically, between 20 and 24. The remaining 6 hextets is where we're going to be manipulating. So like all other multicast addresses, solicited node multicast addresses are also mapped to an Ethernet's MAC address, and we're going to be talking about that. So here's our PVC2 global unicast address and its solicited address. You're going to notice that they're going to be mapping pretty similar. Let me grab my pin. It's 00:0200. Again, notice the double colon there, so there are 2 zeros in the next 2 spots, hence the 00:200. Here is its MAC address. Again, notice we are taking the first 20, or the, not first, but the last or the remaining 24 bits of our MAC address. And here is all of his nice little things. So it's the same for both PCs. Although rare, solicited node multicast addresses sometimes may not be unique. I've not really encountered this, but here's an example where this may occur. Not a problem, because ICMP version 6 name service contains target unicast addresses, which we're going to talk about that coming up. So moving on to the solicited node multicast advantages. So why are solicited node multicast better than broadcast? Multicast can be mapped to an Ethernet MAC address, and the Ethernet NICs can filter these frames. This is a portion for mapping. So why is this a good thing? It's about efficiency. So the broadcast, we're going to send it to everything. So data must be passed to upper layers for processing of that ARP. Whereas with IPv4 and IPv6 multicasting, IP multicasting packets can be filtered by switches, only sending packets to the members of that group. So instead of having to go up to a layer 3 device and then back down, we can send it to the appropriate groups. So here we have IPv4, IGMP, the Internet Group Management Protocol. IPv6 has the multicast listener discovery. So however, the solicited node multicasts are forwarded out all of the ports because of the potential huge forward tables needed to store these addresses. But again, it's about better efficiency. Besides its own MAC address, the Ethernet NIC will accept multicast addresses created from the solicited node multicast address. That would be the global unicast address. The link local addresses, and any assigned multicast addresses such as the all IPv6 devices. So the mapping of this IPv6 multicast is, again, more efficient. So we're building up that. Not quite sure why we do that, but in this chapter, that was a huge thing where we talk about as it's coming up, but we don't discuss it quite yet. So let's verify the solicited node multicast address. You should be able to see it as FF02, typically : 1, and then FF. The remaining 6 hextets will be the appropriate last 24 bits of the appropriate MAC address. Oh, lost my pin. Notice again, they should be matching up. So, member of these multicast groups, again, FF02 is all devices, FF022 is all routers. Here we have our solicited node. We can base that off of our global unicast address, and here we have our link local unicast address. FF02 means link local. So let's talk about a few examples. So I know my IPv6 or my IPv4. So what's the MAC address? It will check its ARP cache, maybe send a ARP request, and then should get an ARP reply. So it's able to then get the appropriate information and sort in its ARP cache. With IPv version 6 address using the ICMP v6 neighbor discovery message, we're going to do a solicitation and a advertisement. That solicitation is going to be via its solicited node. So the device stored this mapping in their neighbor cache. So again, very similar to router discovery in solicitation and advertisements, but here we're doing it between two hosts. So no, my IPv6, what's my MAC address? My neighbor cache, it will send a neighbor solicitation. It will get a neighbor advertisement or reply, stores it in its neighbor cache. Same thing with IPv4 with ARP. So the destination MAC address via a layer 2 broadcast. The Ethernet should be a broadcast, so straight Fs. The ARP message will be the message at the targeted IPv4 address. Again, it's a broadcast, so the frame will forward it out, or the switch will get the frame and will forward it out all ports. Because the Ethernet broadcast has to be passed to upper layers. Layer 2 multicast allows frames to be filtered by the NICs and not have to worry about sending them to an upper layer protocol for inspection. So that was a benefit for the solicited nodes for multicasts for both layer 2 and layer 3 multicasts. So within this IPv6 address resolution, again, we're going to end up with a multicast. Within our next portion, IPv6 will be a solicited node multicast. Notice it will be a solicited multicast based off of the solicited node multicast, which will be based off of the multicast portion of the Ethernet, which will be its frame, which will then get its MAC address. That way we don't have to send it out to additional ports. We can send it just to the appropriate neighbor that we want without having to worry about sending it to an upper layer for more or a deeper protocol inspection. So here we're going to ping a global unique address. It will then send a neighbor solicitation. It should be able to get a neighbor advertisement. Based off of its MAC address. It will then populate the appropriate information in the neighbor cache, both its IPv4 and its MAC address. Nope. That's being allowed us to ping it. So the neighbor solicitation from PC1, if we're doing an IPv4 ARP request, again, notice the appropriate MAC address within the Ethernet 2 frame. Then notice the things for IPv6 for our destination. FF02, FF, and the remaining 6 or the remaining 24 bits, 6 hextets, are going to be the same as our remaining 24 bits in our MAC address. Neighbor solicitation message, our appropriate target based off of our remaining 24 bits, which we got from our solicitation message. For our global unique address, here is our ARP reply. Again, notice the neighbor advertisement. Notice IPv6 sender for PC2. Notice the appropriate MAC address for the sender. Notice the unicast address. Notice the unicast address for our frame. That's going to be our destination frame. So let's talk about mapping our IPv6 multicast to our Ethernet multicasts. Here we have an Ethernet MAC address of 3333. That goes all the way across. So these are going to be more of an assigned and a solicited node. Again, we can map these specifically to specific multicast addresses. So if we do a Ethernet MAC address of 333300000001, that's going to be for all devices. If we're doing it 333300000002, that's all routers, so forth and so forth and so forth. The lower order 32 bits of the IPv6 multicast address map to the lower 32-bit portion of a MAC address. This is going to allow us to do mappings from our IPv6 multicast to our Ethernet multicasts. Why 3333? Because 3333 happened to be Xerox's address. And guess who designed this entire process? So this is all thanks to RFC 7042, part of the historical notes. This was a custom during IPv6 design to use 3 for unknown or example values, and 3333 because, again, the appropriate Xerox address. So here we have our destination multicast address. We have our IPv6 multicast destination address, and we have the remaining portions of the IPv6 packet. Same thing, but a different view. Pay attention to the appropriate MAC address, and you'll notice that, again, our multicast MAC addresses are going to be related to our appropriate IPv6 multicast destination addresses. So remember that all IPv6 unicast addresses also have their appropriate and associated IPv6 version solicited node multicast addresses. I'm going to sneeze. Okay. Again, unicast, whether it be a global unicast or a link local unicast, will all get a solicited node multicast address. Again, it is a mapping to them. Once again, Ethernet NICs and multicast addressings, they will be mapped. Both our unicast address uses it, both our solicited node multicast uses it, and so does our multicast MAC addresses use them. So it can be a global, it could be a link local, or it could be any multicast address such as all IPv6 devices. So last is going to be this multicast listener discovery, which will be the MLD2 or MLD version 2, which is very similar to the IGMP version 2 for IPv4. So hosts use MLD to dynamically register themselves in a multicast group on a particular network. Hosts send listener report messages to their local multicast router, informing the router as to which addresses they want to receive, part of that group management or joining of that group. So here we may have R1 be our listener. So we will start updating R1 with the appropriate groups that we want to be in. So the router configured for the MLD or MLD queries will then listen for those report messages. Routers periodically send out queries to discover which multicast groups are then also still active. Multicast addresses using RFC 3306 unicast prefix base IPv6 multicast addresses. So that was an important one because I have seen that on an exam somewhere, which was the appropriate RFC dealing with the unicast prefix based portions of multicast address, and that's RFC 3306. So a general query to everyone. That could just be, again, to get that listener report to see who's still active. Same thing for leaving a group. It will send a listening done for that group, and it will have to be updated in the MLD query router. And then it should be able to then query that group to see if there's any other active hosts. And then it will then send a query to all PCs, seeing which ones still want to be part of that group. And then it will remove the people that want to leave that group. So we can also do MLD version 2 snooping. So a switch can snoop listening reports from the host and create entries in its layer 2 forwarding table for those ports it's receiving them. So it will send packets from the group out of that appropriate interface. So if another host sends a listener report to the same group, the switch snoops their report and adds them to the existing layer 2 forwarding table. If you want to configure this, you can configure this per VLAN, and it's basically the appropriate interface for the VLAN and an IPv6 MLD snooping query. That's it. In our CCNP route course, we will actually do a little bit more configuring of this, and in CCNP switch, you should also be able to set up MLD version 2 snooping on a switch. So once we have it enabled, multicast messages from a group are only sent out ports with hosts that are members of that group, as received by or known by that switch. Because again, it snoops the appropriate frames and packets. Frames, because it's a switch, as it sends up the things to a router, which then becomes a packet. Remember that the solicited node multicast are forward out all ports because of the potential huge forwarding tables needed to store all of the appropriate addresses. So do keep in mind which ones are allowed to be MLDing and which ones have to be going out all ports. If it's a solicited node multicast address, it's all ports still. That's actually the end of this chapter. So if you want to know more about multicasts and MLDing, we can actually see the IPv version 6 multicast primer created by Tim Martin. This is actually a huge in-depth topic that we just barely touched on. Barely, like very, very, very tip of the iceberg. But that's actually it for this section. Again, all credit goes to Rick Graziani. He wrote and produced both the IPv version 6 fundamentals book and IPv6 fundamentals videos that we are using. Thank you.